Okay, so good evening, everybody. Today is the fourth tutorial session of Fundamentals of Power Electronics. Let's start. So, in our last discussion, we discussed about two very important semiconductor devices, MOSFET and IGBT. We also studied the static and dynamic characteristics of these devices and the power loss calculation, how to calculate the power loss and how to select the heat sink for these devices. All these things we discussed. Today we will be starting the AC-DC converter, which means that the converters which basically converts AC waveforms to DC waveforms, and those are called rectifiers, right? We shall start with the very basic, the most basic rectifier circuit, and gradually we shall go to some advanced level circuitry as well. And today we will only study the diode based rectifiers, and we shall study that how to design a diode bridge rectifier. Okay. Numericals related to the design and related to the rectifier circuit. Okay.
Excuse me, madam.
Yes.
Ma'am,
Yeah,
the voice
tell.
is echoing.
Yes, ma'am, your voice is resounding.
Just a minute. My voice is breaking.
No, ma'am, it's resounding.
It shouldn't because I think if
Ma'am,
two
your voice
mics.
is okay when I turn on the mic, then it echoes.
Uh, okay.
And my question was that may I ask about from last problem solving session?
Yeah, sure. Now is it okay? My voice is okay now? Is it echoing now?
Yes, ma'am, it is fine now.
Okay, okay. Tell. What is your doubt regarding last session?
Ma'am, in the first numerical that was discussed,
Huh?
the numerical was that the MOSFET is off when the pulse is 10 volt.
No.
Ma'am,
The MOSFET will not be off when the pulse is 10 volt. Okay, I will just go to the last lecture. Okay. Um,
Ma'am, sorry for disturbing, but it's still echoing, ma'am.
uh, uh, can you just text it? I'm not getting what is the problem. Just text it in the Teams.
ma'am, the first problem discussed in this.
Ah, wait a minute. Can you see the screen?
Yes, it is visible, ma'am.
Okay, now tell.
Yes, ma'am. In this question, VAB is taken as equals to 10 volt and the MOSFET is off. Why is that, ma'am?
Because so this is the circuit and this is the gate pulse waveform that we are giving to this MOSFET, right? This much you understood that this is the gate pulse waveform that we are providing to the gate terminal of this MOSFET, right?
Right,
Now,
ma'am.
when this gate pulse is high, meaning when the gate pulse value is 10 volt, then what we studied that MOSFET is a voltage control device. So whenever you will give a gate pulse of this like this shape 10 volt, then the MOSFET will be on. Till this point it is okay.
Yes, ma'am.
Because we are providing gate pulse, that's why this MOSFET will be on. And here they have mentioned that MOSFET, they have mentioned that we can assume the diode and the MOSFET to be ideal for this question only, for the first part. So if we assume an ideal switch, then when the moment this MOSFET turns on, then this it shorts this path, right? Like this top point and this bottom point. What is a switch? When it turns on an ideal switch, then it is a short path, right? Short circuit path. So the current that is coming out of this source, it will, because what is the nature of current? Current will always try to follow the least impedance path, right? Whichever offers is the least impedance path, it will follow that path. So as the MOSFET is now shorting these points A and B because it is turned on. So it can, ideal switch can take any amount of current, right? That we studied in the first session. It can take any amount of current, and when it is on, there will be no voltage drop across this switch. So ideally, like this path is short now. So if I just let me just draw. So basically, whenever this MOSFET is on, this path becomes short like this. Okay. So whatever current flows, that will be restricted within this path. It will not go to this path. Why? Because this is the least resistance path, least impedance path. If the current has to go to this path, it will have to flow through this resistance, through this resistance. But compared to that, it is not offering any resistance at all. So that's why it will follow through this path, right? When the MOSFET is on. And when we are withdrawing the gate pulse, then the MOSFET is off, so there is no path for the current. Then the current will flow through from here to this resistance and this resistance. And whenever current flows through this path, obviously there will be no voltage drop across A and B, because now A and B, they are basically the same potential. They are at the same potential, right? But when this is off, then the equivalent circuit becomes like this. This is the open path. Now the current flows through this and this, then we get some voltage across this terminal, two terminals. That's why we say when the MOSFET is on, this is during on condition, then there will be no voltage. But when the MOSFET is off, then there will be some voltage in this in the across A and B. Okay,
Yes, ma'am.
you understood, right?
Yes, ma'am. In the next step, ma'am, 0 0.4. Can you please do the next slide?
Okay. Hmm. Huh. So here I have shown the equivalent circuit, what I just explained to you, that when the MOSFET is on, then the equivalent circuit is like this, because they are kind of like, you can assume they are not present at all, because the current path is from diode to this resistance through this MOSFET again back to the source. This is the circuit when the MOSFET is on. So I have written when gate pulse is provided, MOSFET is on, hence VAB equal to 0. Because this point A, like this is actually point A and this is point B. So these 2 points are at the same potential due to this MOSFET. Fine.
Yes, fine, ma'am.
Okay. And if we go to this slide, then the same thing that I explained, that now I have withdrawn the pulse from the MOSFET. So now the MOSFET is off. There is no MOSFET at this point. Like there is the MOSFET is there, but it is off. So it can't provide any current path. Now the current will flow from here to these resistances. And these resistances are in parallel because these 2 points are at the same potential and these 2 points are at same potential. So they are in parallel. So 2 kilo ohm and 2 kilo ohm, they effectively become 1 kilo ohm. So 1 kilo ohm here and here there is 1 kilo ohm. So the total resistance here is 2 kilo ohm. Okay. The effective resistance. And the diode is like there will be some very minimal drop across the diode also. So whatever voltage is there, that will be getting divided equally across this resistance and across A and B, right? Because here also the effective resistance is 1 kilo ohm. Parallel combination of two resistances, each of which have a value of 2 kilo ohm. Okay, is it fine?
Yes, ma'am.
Okay. Do you have any other doubt regarding any problem?
No, ma'am.
Okay, then we can start today's discussion. Anybody else has any doubt regarding last tutorial session? Okay, so I shall start today's session. So let's start. Now here I have mentioned the term rectifier. What is a rectifier? A rectifier is nothing but a circuit, a converter, which converts AC signals to DC signals. Okay, that is the function of a rectifier. So here you know that this is the symbol of a AC source. So this is a single phase AC source. Suppose if we assume the standard single phase grid, then this will be 230 volt RMS, 230 volt RMS and 50 hertz, right? That is our standard grid. So sorry for the very bad handwriting here. I can't write here very properly. So this is a 230 volt 50 hertz AC supply. Okay. Here what we have placed a diode, a simple diode, and then here we have the load. Suppose this is some load resistance RL we have here. Okay. So what will happen? So the AC supply is what? It will be a sinusoidal voltage, something like this. This is our source voltage Vs. It has a sinusoidal shape. Okay. So here this electrical angle is 2 pi. In this 2 pi it completes one full cycle, right? So this is the source voltage. Now what will happen as we have placed the diode? So when it is the positive half cycle meaning when the voltage, the instantaneous value is positive, greater than or equal to 0, right? In this half, diode is definitely forward biased, right? Because here it is having some positive value here during this portion. I am talking about this portion. So it is getting some positive voltage, right? So it is forward biased. So current will flow like this through the load resistance. Now the diode is forward biased, so it will act like a switch, a closed switch. So current will flow through load resistance. Now what happens in the negative half cycle? As soon as the voltage goes down and it becomes less than 0, then the moment is it becomes less than 0, then the diode becomes reverse biased, right? because now the instantaneous polarity of the supply voltage is like this. Earlier it was like this, but now it is like this, right? Because it has changed the polarity. So now the diode can't conduct. Now there will be no current through the load resistance because this path is open. Now this is open path. The diode can't conduct. So there will be no voltage across the load resistance, right? Because there is no current, so no voltage drop across the load resistance. The voltage will be blocked by the diode, right? In the reverse biased condition. So now the output voltage, we are defining this as the output voltage, right? So the voltage across the load resistance, this is our output voltage, V naught. V naught is 0 during the entire negative half cycle. Is it fine? Right. So this is pretty straightforward. So that's why we call it a half wave rectifier. Why a half wave? Because only during one half cycle we get some voltage, and during the other half cycle we don't get any voltage. That's why it is called a half wave rectifier. This is the simplest form of rectifier you will get. Just one diode. And this is an uncontrolled device. So we call it single phase uncontrolled half wave rectifier. Okay. Now there is a very obvious disadvantage. What is the disadvantage? That although we are getting from AC voltage, we are getting a DC voltage, but half of the time we are not getting any voltage at all, right? We are not getting any voltage. We are getting zero voltage. So our average voltage is very less here because during this entire half cycle, there is no voltage across the load. So therefore, we can think of any circuit where we can have some voltage in the negative half cycle also, right? So we need another modified circuit which can give some voltage in the negative half cycle also. So so that's why we have full wave rectifier. This is half wave. Now we will see full wave rectifier. These two are examples of full wave rectifier. Okay. This one is called split phase full wave rectifier. This one is also called center tap rectifier. This is also I shall mention in the final PPT anyway. So this is also called center tap. I'm not writing because here the writing is not really good. So I will just not write here anyway. This is called center tapped. Okay. What happens here? So here again we have one AC source. Suppose the instantaneous polarity during the first half cycle is this. So here also if we just follow the dot convention, so this is suppose the instantaneous polarities. So then this diode becomes forward biased and the current flows like this, right? In the positive half cycle. In the positive half cycle, okay? During this portion. In the negative half cycle, it becomes opposite. The polarity is now opposite. Here also we can say that the polarity reverses here. This becomes minus, this becomes plus. So now see the beauty of the circuit is that now this lower diode becomes forward biased, right? So now the current can flow through the load like this. And observe one thing that here the current direction is same for both the half cycles. Here also the current flows from this to this. So the voltage drop will be like this. And here also the current flows from this point to this point. So here also the same voltage drop across the load. So here in both the half cycles we can have some voltage, right? And this one is called a bridge rectifier. A single phase full wave bridge rectifier. Okay. So this combination, these two devices, and one of the anodes is connected to the cathode of another device. This is called a half bridge. So two half bridges are there, and this becomes a full bridge. Okay, so this portion is called a half bridge. This is a half bridge. This is again a half bridge. So two half bridges are there. That's why it is called a full bridge rectifier. So here also you can analyze the situation in the same way. We can take, so now this is positive, this is negative, like this is the instantaneous polarity. Now this diode, suppose we name it, this is D1. Suppose this is D4, this is D3, and this is D2. Okay. So when during the positive half cycle, D1 and D2, they will conduct, right? Because here the polarity is positive, so this definitely becomes forward biased. The current goes through this, through load, and it comes back via D2 and again back to the supply. Okay, this is the current path during uh, positive half cycle. During negative half cycle, the remaining two diodes will become forward biased. So the current path will be from here through D3, again through load, and now it will come back through D4, to the source. Okay, this will be the current path in the two half cycles. Okay, is it okay?
Excuse me, ma'am. What is the role of load?
Sorry.
Ma'am, what is the role of load in the circuit?
So so what is the basic like what is the basic requirement of an electrical circuit? There will be a source, there will be a load, and some power will be transferred from source side to the load side. And load can be anything. Load can be like whatever you see in your daily life, there are various electrical loads, right? So most of the times for our discussion, like for the basic preliminary analysis, we assume R load. But obviously, most of the loads are not pure R loads. There will be inductive loads. There may be capacitive loads, like combination of R and L, combination of R and C may be there, or there may be only resistive load as well. Different types of loads are there. There may be RLE load, okay, resistive, inductive, and there may be some constant voltage source at maybe like that. So these loads you see, right? In your daily lives, you see light, fans, or all these things are load only, right? So if you transfer some power from the source to the load, you will get electricity, right? Like you will get the energy in terms of electrical energy, right? And you can uh like that's what load is. Otherwise, if there is no load in the electrical circuit, where will the power go? What is the point of drawing some power from the source? It will be like it will get loaded, it will get delivered to somewhere, right? That is the load where we dump the power. Like that is the load. So, yeah. So these are the full bridge rectifiers. Fine. Yeah. So here I have shown you. So here you, sorry. Hmm. So this is the bridge rectifier. Here you notice that we have the voltage at both the half cycles. This is our source voltage In the positive half cycle, these two diagonal diodes conduct, and we can have this output voltage across the load, which exactly takes the just a minute, okay, just a minute. Yeah, sorry for the interruption. So I was talking about this full bridge rectifier. So here you can see that we are getting an output voltage uh, at both the half cycles, right? Unlike the half wave rectifier, where we were only getting voltage at the positive half cycle and zero during this portion. But here we are getting identical shaped voltage in the negative half cycle as well. So basically, if you just flip this one, flip this portion to the positive axis, then you will get this kind of voltage shape. This is they are basically the mirror images, right? From this negative half cycle voltage, you are just flipping it. So diode is doing nothing, just flipping this negative voltage to the positive side. Another point to be noted here is, although we are getting a DC voltage, but still there are some pulsations, right? They are not pure DC. What is a pure DC? A pure DC will be if this is our time axis, suppose. So a pure DC waveform will be something like this, horizontal to the time axis, right? But here the waveform is not like this. It is basically having a sinusoidal shape only, but at the positive axis, right? From the negative side, it just flipped to the positive side, but there are still some pulsations. So if you just do you guys know Fourier analysis? Have you studied? So if you do the Fourier analysis of this waveform, so you will get, so suppose this is your V0, right? So V0 you will get some DC term, okay? So the term will be 2 by pi Vn, that you can calculate. You can calculate by yourselves from the formulas, and afterwards you will get some sine terms, right? Uh, Sine terms. Sine, like Fourier series is what? Where we can represent a signal in terms of its DC value and also some sine and cosine terms, right? Of fundamental frequency and multiples of fundamental frequency, right? Like 2 times, thrice, 4 times of fundamental. Here the fundamental frequency is 50 hertz. So, so here the fundamental frequency is 50 hertz, right? 50 hertz. So you will get the sine and cosine terms in terms of the multiples of 50, right? 50 like 100 hertz, 200 hertz, right? So you can check for yourselves. You just do the Fourier analysis and check which terms you get from this kind of waveform. Okay. The average value is 2 by pi Vn. Okay. So there will be some average and along with that some sine cosine terms. Okay. This is our full wave rectifier. So here I have shown how should we determine which diodes will conduct. So in any circuit, how will you determine which diode will conduct in a particular situation, right? So this diode, they are a nomenclature is here. This is first diode. This is 1, 3, 2, and 4. Okay, and these are the load terminals. So there is something which we call the common anode configuration and common cathode configuration. Okay, what is common anode configuration? Here, if you see for diode number 2 and diode number 4, here their anodes are at the same potential, right? Their anodes are at the same potential, but their cathodes are connected to different points, right? The cathode of this one is connected here, and the cathode of this one is connected here, right? Similarly, if you see the top two diodes, here their cathodes are at same potential, 1 and 3. They are connected to the same point electrically, but their anodes are at different points, right? So this one is called common anode configuration. This one is called common cathode configuration. So suppose you have an AC voltage here. So the diodes which are in common cathode configuration, for them, whichever diode will have the maximum positive voltage, okay, that diode will be forward biased. So suppose they are in common cathode configuration, and during and this is the source voltage, suppose. So during this positive half cycle, during this portion, when the sine wave is greater than 0, okay, during this portion you can understand that this the potential at this point, the anode of this diode, it is always greater than this one, right? Because the positive point in the here, it is directly connected to the anode of this diode. So this diode will be forward biased, but this diode will not be forward biased. Okay. Similarly, when there is common anode configuration like this bottom one, or like this circuit is just a rearrangement of this circuit. They are the same circuits. So in common anode configuration, it is the opposite. Whichever diode will have the lowest potential in the cathode terminal, that will be forward biased. So during this positive half cycle, this diode is forward biased and this diode is forward biased. Okay. And in the negative half cycle, again, so the polarity reverses. Now the positive terminal is connected to this diode. So this diode is forward biased, and this diode has the lowest potential among these two. So this diode will be forward biased. Okay. So here the two diagonal diodes conduct simultaneously, 1 and 2 and 3 and 4. Okay. Is this clear?
Yes, ma'am, an idea.
Sorry, please repeat once.
Yes, ma'am, got an idea.
Okay, okay, okay. So, yeah. Here, there is an additional component. The additional component is this capacitor. We have our AC source, we have the diode full bridge configuration. We also have our load resistance. Along with that, in parallel with the load, we have a capacitor. Okay. So why are we adding this capacitor? Earlier, I was telling you that although we are getting this, like we are converting the AC signal to a DC signal with the help of this diode bridge rectifier, but we are getting a pulsating DC, right? There may be some load which requires very stiff DC. Stiff DC means which have to be necessarily a pure DC, like very stiff DC voltage. There will be not much pulsation that the load can withstand. Okay. We will have to design our converters based on our load requirements, right? So there may be a load which doesn't allow this kind of voltage pulsations. There we need to have a constant DC. What will we do now? Because applying this converter, we can only get this kind of voltage. So that's why we need to add one capacitor, right? What will the capacitor do? So that's what I have shown here. So this was the earlier rectified voltage, right? Where we were getting sinusoidal voltages but flipped to the DC side. Now, if you add the capacitor, the output voltage steady state waveform will be like this, not like this. It will become something like this. So what is happening here? So basically, suppose if you start at this point, this is the peak point of the sinusoidal wave, right? This is the peak point. So from this point, if you see, the source voltage is decreasing from this point. But capacitor doesn't allow very sudden change of voltage, right? This is a steady state waveform, mind please. This is not a transient waveform. So from this point, when the voltage dips from this value, the capacitor voltage will not follow this waveform. It will start discharging. So from this point onwards, the capacitor starts discharging and it discharges till this point. What do you mean by discharging? Discharging means now the capacitor itself provides the load current. So from the capacitor, the load current flows through the resistor. Okay, through the resistor. That's how the current flows. And during this portion, the diodes don't conduct. Okay, the diodes are not conducting at this point. The capacitor only provides the load current. Okay, till this point. At this point, but the source voltage is as it is. There is no change in the source voltage. It is still sinusoidal. But due to the addition of this capacitor, we are getting this kind of load voltage. Okay. Now at this point, what happens is now as the capacitor is providing this current, so definitely there will be some dip in the capacitor voltage. So here at this point, it was at this point. Sorry. It was at this point. After discharging, it reaches at this point. So some dip in the output voltage occurred. Now, the moment this voltage is slightly lesser than this instantaneous source voltage, which is happening here. So here the source voltage was increasing. Okay, source voltage was increasing, and at this point they are same. So now the capacitor and then the source voltage will continue rising and the capacitor voltage is now lesser than the source voltage. So now the capacitor will get charged during this period. During this period, the capacitor will get charged. During this period, the diodes will conduct, right? So during the positive half cycle, this diode and this diode will conduct as we already saw 1 and 4. So the current will be from the usual path from this diode through this capacitor, okay, and this load, and again back to the source through this diode during this charging period. That's why the output voltage resembles the shape of the source voltage during this portion. But again, when the capacitor gets charged to the maximum grid voltage, like the peak point, then the source voltage again starts reducing, but the capacitor voltage doesn't allow this drop of voltage. It discharges and it provides to the load resistance, right? So this is the cycle. And this is the advantage of providing a capacitor. This acts as a filter. What it is doing? From this kind of voltage shape, it is providing us this kind of voltage shape. So this is much better voltage than this one, right? Because this is closer to our ideal DC voltage than this one, obviously, because it has very low ripple. This variation in voltage is much smaller than the earlier variation in the voltage. So that's why we provide a capacitive filter. Okay. Now what will happen to the source current now? What will happen? So suppose what you were doing at the beginning, when you are suppose turning on this circuit at the beginning, the capacitor is not charged, right? It doesn't have any voltage across it. So this is the steady voltage, steady state voltage waveform. But at the starting, when you are just starting this converter, there is no voltage across this capacitor, right? So here you are applying one voltage, there is one voltage source, and you were just like connecting the capacitor to a voltage source, uncharged capacitor, right? You are connecting the uncharged capacitor to the voltage source. What will happen? It will draw huge amount of current initially. So that's why the source current waveform, this is the this I current, and the source current here is just the this is just the AC waveform. This is IS, and this is the current waveform at this point, because it has been flipped. Just like the voltage, we have flipped this current waveform. So this kind of peaky current will get drawn from the source. Why? Because you are connecting a capacitor, which is again a kind of, you can say, a voltage source in parallel with another voltage source, and they have difference of voltage, right? So when you parallel two voltage sources which have difference in potential, then obviously a huge current will flow from the higher potential one to the lower potential one, right? So that's why in the initial stage there will be very huge peaky current, very huge current, and at the steady state also the current shape will be like this, but the magnitude will reduce, but it will still be a peaky sort of current. Okay, this is the current at this point, like at this node, and this is the source current that is getting drawn from the AC source. Okay, so this is a disadvantage. Okay, so there are some protection circuits to restrict this current magnitude. Otherwise, the diodes may get blown. So that will be discussed later. But that's how the current looks when we add a capacitive filter. Is this understood till this point?
Excuse me, ma'am.
Yes.
Ma'am, isn't a capacitor a non-dissipative passive device?
Yeah. So there is no power dissipation is happening, right? Power dissipation is not happening because if you see, there will be so the voltage across this capacitor, that will be a DC voltage, but ideally the current through a capacitor in steady state, it will never have a DC component, right? In steady state, the whatever current flows through this capacitor, it will always be AC in nature. So a DC voltage multiplied by a AC current, it will not result in any power dissipation, right? So power dissipation is zero, but some current will flow through this, right? Otherwise, how this kind of voltage you will generate? It will take some current, but that current will be AC in nature, and the DC portion of the current will flow through the resistance. Okay, so this is a resistive load. So you know now the voltage shape is like this. So the current shape will also be like this, same. The current, because this is a resistive load, so the current will have similar shape, just that it will have a different magnitude. So that will be your V naught by R. Whatever current will flow, that will be V naught by R, the load resistance value. So this DC current will flow through the resistor and the AC portion of the current will flow through the capacitor. Okay. So DC, so there is no power dissipation in the capacitor. The only power dissipation will be in the resistance. Okay. So ideally, capacitor and inductance, all these passives, they don't dissipate any power. They are non-dissipative elements. But if you see practically, if you get a practical capacitor, so the capacitor model is not a simple capacitor. There is something we call a ESR. Okay, so sorry, just a minute. So this is not in the scope of this session, but anyway, I will just tell for the sake of the discussion. So if you see a practical capacitor, so this is our ideal capacitor, a pure capacitance, right? No dissipation, no power dissipation at all. But actually, there is a series resistance that is in series with this capacitance, okay? That we call ESR, equivalent series resistance. Although this value is usually very small, this series resistance value, but due to the presence of this ESR, there is some small portion of dissipation that happens here. Okay. So there is ideally it should be zero, but practically there is some small amount of dissipation that happens. Similarly for inductor, ideally there is no dissipation in an inductor also. But when you make an inductor, you will have to give certain turns, right? Around the core, there will be a core, and around that core, you will wind some wires. So those wires will have their own resistance. So the practical model will be a resistance in series with an inductor. So again, there will be some power dissipation in this resistance. Okay. So practically, there is no element where there is zero loss. Fine. Okay. So let's proceed. It is okay, right? You guys understood now? Okay. So now we will go to the problem solving part. Let's start. So the first question is, what are the advantages of a diode bridge rectifier with filter capacitor? So there are these four options. So correct options I have already pointed, high volumetric efficiency and low component count. And other two options are low power factor and high initial current. So definitely these 2 points, they cannot be advantages, right? Because low power factor is no way good. If your power factor is poor, then that is not an advantage. That is a disadvantage. Similarly, high initial current means if it initially draws a very large current, that is not good for the circuit. It can damage some components, some devices of the circuit. Okay, so that is not good for the circuit. So these two, A and C, these are the advantages. High volumetric efficiency means that diode bridge converter is very compact. It takes a very small space. Its volume is small. That is why it has high volumetric efficiency. So from a very small amount of, like for a very small volume, you can extract high amount of power, right? So that's why it has high volumetric efficiency. And low component count means, low component count means it needs very minimal components, only four diodes and a capacitor maybe. So that is like that is very less. Okay. So low component count, that means that it will not be very expensive. The lower the component count, the lower will be the cost of the circuit. So these are the two advantages of a diode bridge rectifier. Now let's go to the next question. Yeah. So what they have asked? They have asked that consider the diode bridge rectifier circuit shown in this figure. If 230 volt 50 hertz AC input is given to the rectifier circuit, so this is the input specification 230 volt 50 hertz, where input voltage can vary in the range of plus minus 10%. Calculate the peak inverse voltage rating for the diodes in volts. So we say that our standard voltage is 230 volt RMS. This is the RMS voltage, okay, RMS value. So the peak will be 230 root 2, right? For sinusoidal quantities, we know the peak value is root 2 times the RMS value. But this value is the standard value, okay? But sometimes we know the grid voltage value can fluctuate, right? Grid voltage, because with grid there are various kinds of loads that are attached to the grid. So sometimes the grid voltage may rise and sometimes it may dip also. So that's why there is a tolerance, there is a range plus minus 10%. Okay. So the grid voltage can be up to 230, 110% of 230, and it can dip to 90% of 230. That's what they have said here, that it can vary in the range of plus minus 10%. Now we need to find out what will be the peak inverse rating of the diode, right? So each diode, so the peak inverse rating will be similar for each of the diodes, right? So what will be that you need to find out. Okay. So we can take a 4-minute break now. Okay. Meanwhile, you can think of the answer. What could be the answer of this? And you can tell me. Okay. We will return around what is the time now? It is 6:54, right? At around 6:58, we will return. Okay. So you can think the answer what it could be. And if somebody calculates it, you can tell me. Okay. Okay, let's start. So, what? So, can anybody tell me how to calculate the peak inverse voltage rating of the diodes?
And from its formula,
Yeah, I know from the formula, but what is the approach? How will you formula though is it's okay, but you don't need actually any formula. There is no formula for calculating the peak inverse voltage as such. You just have to determine what is the maximum voltage each diode has to block when it is reverse biased, right? So if you know what is the voltage that it needs to block, then that is the peak inverse voltage, right? The maximum value of voltage that each diode needs to block. That is the peak inverse voltage rating of a diode. Okay, so let's see how we can calculate that. Yeah. So there are four diodes, right? So as I already mentioned that when during the positive half cycle, this is the positive half cycle, right? So during this portion, suppose this is D1, this is D3, this is uh, D4, and this is D2. Okay. So during positive half cycle, D1 and D4 conduct. D1 and D4. These two diagonal diodes, they conduct. And during negative half cycle, the other two diagonal diodes conduct. D2 and D3. Fine. D2 and D3. Okay. So this is my source voltage V. This is V. Now, suppose now we are in the positive half cycle, D1 and D2, they are conducting, right? So like this is the current, this is the path from here to through the load, and then again through the through D2 and here. Okay, and capacitor current is also there. Okay. So now what will be the voltage that D3 and D4 has to block? Now they are reverse biased, right? During the positive half cycle. So they will have to block some amount of voltage. What will be that? So if you see this point, this point is connected to this point via this diode, right? Because now this diode is conducting. So this potential comes at this point, and this potential already connected to this point. So essentially, what is the voltage that this diode is blocking? This diode is blocking this voltage, right? Because this is the source voltage. This is the source voltage. This point is connected to this point, and this point is connected to this point. So this point is connected to the anode of this diode, and this point is connected to the cathode of this diode. So what is this voltage? This is basically the source voltage, right? It is blocking source voltage. Now the source voltage is not constant. It is starting from 0, and then it is increasing, it is reaching its peak, and then again it is decreasing. So this is not a constant voltage. So what voltage should we take? We should always take the peak voltage, right, for the safety. So what is the peak voltage that the diode has to block? That is at this point, right? When the sinusoid reaches its peak. And that peak voltage is root 2 times VRMS, right? We know the peak value of the sine is root 2 times VRMS. Now the catch is, here they have given this range plus minus 10%. So what they are trying to say is that although we have given that my voltage is 230 volt, but it can somehow increase from 230 volt to up to 10% of 230 volt, right? That is the point of this range, that it can be plus 10% also, it can be minus 10% also, like it can dip to, right? So that's why we have multiplied 1.1. So that is basically 1 plus the range, like which is 10%, right? So 10% means 0.1. So that's why we have taken 1.1. That gives us the peak inverse voltage of the diode. That is the peak inverse voltage. It, from the name itself you can understand that peak inverse voltage, the peak voltage, that is that the diode needs to block in the reverse biased condition, and the value is 357.796 volt. Okay, VRMS we have taken 230, it is already mentioned, and 1.1 is due to the range given to us, because they have said that grid voltage can vary up to in the range of plus minus 10%. We have not taken minus 10% because obviously if it can take root 2 into 230, it can also take root 2 into 230 into point 9, right? So that is lesser than this. So it can take this much, then it can also take lesser than this. But we will have to the greater side of the voltage because that will be our maximum voltage. That's why we have taken 1.1. Clear? Okay. So this is very easy, right? This question was really easy. Now we will go to this question. So basically, what they are saying here, they are saying that if a single phase diode bridge rectifier shown in the figure is connected to a purely inductive load, then find the conduction angle of the diode D1. Okay. So this load is, suppose you assume it as a constant current source. Okay. To assume it as a constant current source. Suppose, yeah. So there is no change in the current. This is a constant current source. Okay. Now, if this is the current in the load, then what will be the, they have asked for the conduction angle of the diode D1, right? So if the current is like this, then obviously the current drawn from the source will be like this, right? the current drawn from the source will be like this. So I won't say this is a purely inductive load. This is a different question. I should just assume this is a constant current source. A constant current source, okay? I will rectify this. This is a constant current source. We don't know whether like what is the actual load. This is just a constant current source. So the source current will be something like this. Okay. Because here the current will have to be something like this. So here again, this diode and this diode, they conduct in the positive half cycle, and this diode and this diode, they conduct in the negative half cycle. So what is a total electrical angle? The total electrical angle is 2 pi, right? That we already discussed. This angle is 2 pi. This is 2 pi. So what will be the conduction angle of D1? So D1 conducts during the positive half cycle. So this duration is pi, right? Half of 2 pi. So this is the correct answer, pi. This is the correct answer. Okay. So I have shown this only. So this will be our voltage, and this will be our current, right? So D1, D2 in the positive half cycle, and D3, D4 in the negative half cycle. So the duration is pi. This is the duration of conduction angle means what is the angle during which the diode conducts. So that is pi. Okay. So the third problem, sorry. So this is the third problem. Okay. So, yeah. So the next problem. Um, in the diode bridge rectifier circuit shown in figure, the current expression is given. This is the current expression. This current is I. So the current expression is 10 plus 0.2 sine omega t amperes. Average value of load current is 10 ampere. What will be the approximate value of the capacitor current marked in the figure? So this current gets divided between the capacitor and the load, right? And they have told that the average value of the load current is 10 ampere, and current at this point is current through this branch is this one. So what will be the current through this capacitor? What is IC? So can anybody tell what will be IC? This is very easy. You don't have to calculate anything. There is no calculation in this question.
I'm 10 ampere.
No, actually, see what they have
Option
given
C.
that. Yeah, option C. That is the correct answer. Can you please explain why option C is correct?
The question itself, they given the current expression is 10 plus 0.2 sine omega t.
Right.
10 is the load current.
Yes.
The I should be the sum of IC plus I naught.
Right. Correct.
So 0.2 sine omega t.
So this is straightforward. See, this current I, this is the summation of this capacitive current and this load current. I is equal to IC plus I naught. Now they have mentioned that the average value of load current is 10 ampere, right? So in this current expression also, if you look at it, there is 10 plus some sign quantity. So obviously this DC portion, this constant part will flow through the load, and rest of the portion will flow through the capacitor, because this is a sign quantity, this is a AC quantity. So the current flowing through the capacitor will be 0.2 sine omega t. I mentioned earlier that in steady state, a capacitor can't take any DC current, right? Current through a capacitor will always be a AC current. So this can never flow through this capacitor. This is a pure DC current, right? So suppose the waveform is what? There is this pure DC, this is 10, suppose this value is 10, and over this there is some small amount of sine quantity, right? This is the current, total current. So obviously this DC portion will flow through the load, and this small portion, this AC portion will flow through the capacitor, right? If this is my I, this is my I, okay, and this is time. Fine. So there is no calculation at all. Just seeing the question only you can answer. So I have explained it here, just whatever I said just now, that the DC portion of current flows through the resistive load and the AC part flows through the capacitor. And I is the summation of I naught and IC. So IC is 0.2 sine omega t. Okay. Option C. So let's go to the next question. Yeah. So here what they have said, the output voltage waveform for the circuit is shown in the figure. So this is the output voltage waveform, right? This bold black one, this is the output voltage waveform. VM1 and VM2 are given. This is VM1 and VM2. The values are given. Find the energy lost by the capacitor during discharge period in joules. So we already discussed what is our output voltage waveform, what should it be during when we apply a capacitive filter, right? When we place a capacitor in parallel with the load. So this is the output voltage becomes something like this. So this is the charging period when the output voltage follows exactly the source voltage, and then there is a discharging period when the output voltage doesn't follow this source voltage. Here the source voltage is falling, but output voltage is not falling. It is retaining some value. Right. This is the discharging period when the capacitor provides the load current. Right. So they are asking, find the energy lost by the capacitor during discharge period, during this period, from this portion point to this point. So can anybody tell what will be the process to find out the energy loss? So anybody has any clue how to proceed? Okay, so let's just discuss it. Fine. So earlier you understood, right, how we are getting this kind of output voltage, because the capacitor is retaining some charge. It is whenever the capacitor voltage falls below the supply voltage, it charges till it gets to the peak value of the supply voltage, and then it discharges, right? Until the next point when again it falls below the supply voltage and it charges, and this cycle follows, right? So here they have given the values of VM1 and VM2, right? These 2 points, this voltage value, that is the peak value, and VM2. What is VM2? The VM2 voltage value is the minimum voltage of the output, the minimum point of the output voltage, right? So there is some small pulsation in the output voltage. This is charging, and getting to the peak, and again the discharging period starts and it falls to this point. This is the minimum point. This minimum point is VM2, which is 190 volts, right? So we know what is the energy stored in a capacitor at any point of time. That we know, right? What is the energy stored in a capacitor? If the capacitance value is C and the voltage across that capacitor is V, what is the energy stored in a capacitor then?
And half is equals to no, E is equals to 1 by 2 CV square.
Right? Half CV square. That is the value of the energy stored in a capacitor. So now things are very easy. At this point, we know what is the voltage value, right? At this point, the voltage value is Vm1, that is given. And we know our capacitance value is 1.5 millifarad. Again, at this point, we know what is the value of Vm2. This is the final point, right? If this indicates the starting of the discharging period, this indicates the ending of the discharging period. So we know the initial voltage, we know the final voltage, and we know the capacitance value. So we have all the data, right? It is simply delta E is half C into Vm1 square minus Vm2 square, right? So this is the initial, so this is the initial voltage, and this is the final voltage. Actually, this is final minus initial. We are just like, we just to get a positive value, we have just written Vm1 square minus Vm2 square. This is the energy lost, right? This is the energy lost. So I have just put the values 1.5 millifarad and 200 square minus 190 square. So that comes out to be 2.925 joule. Fine. Is it okay? We are just calculating the delta E. So this is at starting of this discharging period, we have the E. Ending of the discharging period also we have some E, right? It is not zero. Some value of E is there because some value of voltage is still retained by the capacitor. So, so by doing this half C, V1 square minus V2 square, we get the delta E. Okay, fine.
Excuse me, madam.
Huh.
And why we delta E?
Because this is the energy lost during the process. So at this point, there is some absolute E. Suppose that is E1. And at this point, there is some absolute E that is still retained in the capacitor. There is some energy that is still in the capacitor, right? If the energy becomes zero, then there will be no voltage at all. But there is some voltage, right? It is not zero. So that energy is E2, suppose. So what is the difference? E1 minus E2, right? E1 is greater than E2 because here the voltage is higher. At this point, the voltage is higher than this point, right? So the what is the difference? The difference in E, that is the energy lost, right? During the discharging process. It had certain amount of energy, and as it discharged, it lost some energy. Right. So the difference in this point, energy in this point and this point, that is the energy lost during discharging period. Okay. Okay. So fine. Let's go to the next problem. Yeah. So what is the problem? What is the correct average load voltage across the terminal AB terminal as shown in the figure below? Consider the diode is ideal. Right. So there is this AC source that is given as Vm sin omega t, and there is a load resistance. This is point A, this is point B, and the diode is connected like this. So they are asking what will be the average voltage across A and B. And they have also mentioned the polarity. So this is the polarity. So the voltage is, the potential difference is potential between this to this, right? A to B. we need to find the average voltage. So now, see, let's understand first what will happen. So, the same source voltage that we are seeing again and again, the same source voltage. This is our V in, right? And this is our peak value, which is Vm, right? So this value is Vm, right? This is Vm. Now you can see during positive half cycle, so this is our polarity, instantaneous polarity. So is the diode reverse biased or forward biased during positive half cycle?
Reverse.
Reverse biased, right? Because the positive potential is coming at this point. This is the cathode terminal. This is the cathode terminal. This is the anode terminal. So definitely the diode is reverse biased. It will not conduct. So there is no current in the circuit. So there is no voltage across the resistance, right? The resistance drop is what? Simply IR. So if there is no I, there is no V. In the negative half cycle, in the negative half cycle, what happens is this diode becomes forward biased. Why? Because now the polarity has changed to this, and now this positive potential comes here, and the diode becomes forward biased. The current will flow like this. Okay. Current through diode always flows from anode to cathode, that we have seen. This is the current direction. So the current comes through this point like this, and like this. Fine. So as the current flows from this point to this point, the voltage drop becomes here. The voltage polarity is positive compared to this point, right? This point becomes more positive than this point, right? That we have understood. So first of all, what will be the voltage shape? The voltage shape will be during positive half cycle, no voltage, so 0. And during negative half cycle, it will exactly follow the source voltage, but like this. Why? Because in the question, they have already mentioned this is my positive, this is my negative. But due to this current direction, we are getting this point is having more, this point is positive than this point. So this is our voltage, right? This is our output voltage. And what we need to calculate is, we need to calculate the average value. This is the wave shape with respect to time. Okay. We need to calculate the average value. How do we calculate the average value? Very simple. We all know how to calculate. So that's what I have shown here. This is the voltage from pi to 2 pi. And average, calculating average voltage is like the usual formula. 1
Ma'am,
by the
could you please explain again?
okay. So this much you understood, right? That when it is positive half cycle, the diode is reverse biased, and when it is negative half cycle, the diode is forward biased.
Yes, ma'am.
Okay. So as soon as the diode becomes forward biased, current will flow from the source. So it will flow in this path, right? It will flow from the source. Now this is the positive polarity in the negative half cycle. This point becomes positive, this point becomes negative. So current will flow from this, through this, through this, through the diode back to the source. Fine?
Yes, ma'am.
Yeah. What I'm trying to say is that they have asked us what is the voltage across A to B terminal. So they have said, like, you follow this convention. You assume this point is positive and this point is negative, right? They have asked us
Yes,
because they have already mentioned this point is positive, this point is negative. But as we are analyzing the circuit, we are seeing the current is flowing from B to A, not A to B. So according to our like usual convention, B should be positive and A should be negative, right? Because current is flowing from this point to this point. If the current would have flown from A to B, then the polarity would be like this, as they have mentioned, right? But it is not like that. It is becoming like because current flows from higher potential to lower potential, right? That we know. So according to our knowledge, B is B has a more positive potential than A point, right? That's why we are seeing that this point is positive, this point is negative, and that's why we are drawing the output voltage something like this in the negative region.
Yes, ma'am. Ma'am, we are considering the voltage only when it is forward biased. Diode is
Yeah,
forward.
yeah, because only then the current will flow, right? And
Yes,
then
ma'am.
only we will get some voltage across the resistor.
Yes, ma'am.
Otherwise,
Thank
if
you.
there is no current in the circuit, then there is no voltage drop across the resistance, right? So there is no voltage. That's why it is zero in the positive half cycle.
Okay, ma'am.
And so now we need to calculate the average voltage. So average voltage is like simply the this formula. We have to divide it over the total duration, and because we only have voltage from pi to 2 pi, from 0 to pi it is 0, so I have not mentioned it. From pi to 2 pi we have v0 d omega t. V0 is what? Vm sin omega t, right? From pi to 2 pi. So this comes out to be minus Vm by pi. So this is a negative average voltage. But as I mentioned that it is, we are saying it is negative only because they have already mentioned in the question that you assume this terminal is positive and this is negative. If it was not mentioned prior, then we could have said like it is positive also. This is just a matter of convention, nothing else. Okay, don't be confused by it, like why it is negative, why it is positive, what is this. It is just because they already mentioned you take this point as positive and this point as negative. It was mentioned in the question itself. That's why we are saying, but as the current is flowing through this from B point to A point, that's why it should be positive instead of negative. And that's why we have seen we have got a negative average value. Okay, that's it. Okay, so fine by everybody.
Excuse me, ma'am.
Yes.
Yes, ma'am.
Even if the polarity is not given, the circuit will not conduct because it will be in reverse bias.
So polarity has nothing to do with the forward bias or reverse bias condition. Okay. So you can take anything. If it was not mentioned, you can take your own polarity. You can take this is positive, this is negative. But the biasing condition is dependent on the voltage polarity, right? When what is the potential at this point at the cathode point, and what is the potential of anode point. So diode will see, okay, now my anode potential is higher than my cathode potential. So now this is a forward bias condition, okay? And when it is the opposite, this potential is more and than this. So when cathode potential is more than the anode potential, then the diode will see that, okay, now this point is more higher than this point. So this is a reverse bias condition and this will be off. This will be a open path, and there will be no path for the current to flow because this is open. So the this convention, this sign, all these things has nothing to do with the diode. The diode will only see whether it is a forward bias condition or a reverse bias condition. And based on that, the circuit will be a closed circuit or a open circuit. Okay. Okay, let's proceed. So they have asked that the same circuit, a capacitive filter is added across the load side in the figure of question 6. Calculate the average current through the capacitive filter under steady state if Vm, all these values are given, Vm, capacitance, R, like CR, all these values are given, okay. So what they are asking, they are saying that now we have added a capacitive filter across the load. So now you tell me what is the average current through the capacitor. Here also there is nothing to calculate. You can straight away say what should be the average current through the capacitor. Can anybody answer what will be the average current if there is a capacitor connected like this across the load? Okay, so uh, just let me explain. So just tell me one thing. If there is a signal which is pure AC, like it can be of any shape, right? It not sine or cosine, any shape. But suppose this is pure AC. What I mean by pure AC? A pure AC signal means the area under the positive half is equal to the area under the negative half, right? That is called a pure AC signal. So for a pure AC signal like this, any random shape it may have. So what is the average value of a pure AC signal?
Vm sin omega t.
Vm sin omega t is the expression, right? It is the signal expression. But what is the average value? What is the average value of this signal?
2 pi.
No. Average value is basically the DC value. What is the DC value? Okay. So the DC value of a pure AC signal is always 0. Okay. There is no DC component. If you see a sinusoidal signal, is there a DC component? There is no DC component because here positive the area under the positive half is equal to the area under the negative half. There is no DC component in this signal. But if I draw a signal like this, suppose I have a signal like this, then it has a DC component, right? Because here the positive half is greater than the negative half, the area under the positive half. So there will be some DC component along with and over that some AC is superimposed, right? Could you see the difference how I drew this here? This portion and this portion, they are equal, but here the positive portion is more than the negative portion. So it has some DC quantity over which some AC is superimposed. So this DC portion, this is called the average value of this signal. Okay. So for a pure AC quantity, there is no average. The average value is 0. If you compute the average value of a sine wave like this from 0 to 2 pi, what you will get? You will get 0, right? If this is a if this is only if this is a pure AC quantity, right? So instead of pi to 2 pi, if you have 0 to 2 pi, okay, and you write here Vm sine omega t d omega t, you will find 0 because the average is 0. There is no DC component. And we just discussed that whatever current flows through the capacitor in steady state, it never has a DC component because capacitor blocks DC, right? We know that capacitor uh, doesn't allow DC current through it. So simply the average value will be 0 in steady state. You don't have to calculate anything. If you know, this is a one line answer. The average value of current through the capacitive filter is 0. Understood? Why it is like this? Okay, so
Ma'am, this is a property of capacitor.
yeah, so capacitor doesn't allow any DC current through it in steady state. When it is building up voltage, then it may allow, but when it has reached steady state, there is no DC current can flow through the capacitor. And for inductor, it doesn't allow any DC voltage, like any average component of voltage through it. Like the in the voltage, like the average voltage across an inductor should always be zero. And for capacitor, the average value of current over a cycle should be zero. These are the fundamental properties of capacitor and inductor. Okay. Okay, so let's see. For the circuit and waveform given below, the output has a voltage ripple of 5% of input peak voltage. Okay. So they have told that my output voltage ripple is 5% of input peak voltage. What is voltage ripple? That we will see. Assume all the switches to be ideal. That means that all the diodes are ideal. Calculate the discharging period for a capacitor in degrees. Discharging period means this duration. We already saw what is the discharging period, right? When the capacitor discharges from here to here. That time it provides the load current. That is the discharging period. So we need to calculate this angle, right? So there are some annotations. This is 0, then this angle is alpha. This is pi by 2 obviously because this is the peak point of the sine. Then this is pi obviously. Then pi plus alpha. And then again like the same cycle repeats, right? And this is 2 pi. Okay, this is the actual output voltage, right? And this is V naught. Okay, so let's see. So
Ma'am,
first
alpha
of,
denotes
sorry.
alpha denotes the conduction current or the current that goes in the capacitor.
No, it is not current. This is angle. See, this x-axis is omega t. So this is the electrical angle, right? So all this alpha, pi by 2, they are electrical angles. They are denoting some angle. So alpha is the angle from which the capacitor starts charging. And after charging, when it reaches to the peak point, this is the angle pi by 2. Pi by 2 means electrically it is 90-degree angle, right? You know, I think that pi by 2 is basically 90-degree and pi is 180-degree, right? This is in radian. So they are all angles. After pi, again this cycle repeats. So now it is pi plus alpha because already pi angle we have come to pi angle. So this is pi plus alpha. And again this will be pi by 2 plus pi. So this will be 3 pi by 2. This is not written. And this is 2 pi. Okay. So these are angles. So now so we came across a term voltage ripple. Okay, what is a voltage ripple? So voltage ripple is this one. So the output voltage is varying like this, right? So the difference of maximum output voltage and minimum output voltage, this portion is called the voltage ripple. Ripple means what is the pulsation in the voltage. So even though we are using a capacitor, still there is very small amount of pulsation. It is increasing, then it is decreasing, again increasing, again decreasing. But obviously it is much lower than the voltage which we would get if there was no filter. But still there are some small pulsation and that pulsation, the if we quantify this, that is called a voltage ripple, right? This is nothing but the difference of maximum output voltage and minimum output voltage. Okay, that is voltage ripple. So they have written that my voltage ripple is 5% of my input peak voltage. Okay, input peak voltage. So input peak voltage is what? Root 2 times Vrms, right? Root 2 times Vrms. That is my input peak voltage, right? So now I know what is my voltage ripple. My voltage ripple is 0.95 Vm, right? If this is Vm, if this is Vm, then my voltage ripple is 0.95 Vm. And if this angle is alpha, then we can easily say that Vm sine alpha equal to 0.95 Vm, right? Why? Because you see, if this is Vm, this whole height, this is Vm. So Vm is the maximum value of the output voltage, right? Because this is my output voltage and its maximum point is Vm only, right? This height is Vm. And the minimum point is what? My Vmax minus V ripple, right? Vmax minus, if we do V ripple, that is delta V, then we will get our V minimum, right? This point. And delta V, we already got that delta V is 0.05 Vm, right? Because 5% of input peak, that means 0.05. So if we negate this delta V from Vmax, we will get 0.95 Vm, right? This is the point. And at this point, what is the value? That is Vm sine alpha, because this is a sine wave, right? So the expression is what? Vm sine theta, right? So at this point, my theta is alpha, my theta equal to alpha, and I know what is my magnitude. My magnitude is 0.95 Vm. So from both the sides, we can cancel Vm, and from there we can find out what is alpha. Alpha comes out to be this value, right? 71.805 degree. So now we can find out the duration of discharging. What is the duration? It starts at pi by 2 angle and it ends at pi plus alpha angle. So what is the duration? Pi plus alpha minus pi by 2, right? That is the duration. Simply. Is it understood that already pi by 2 has occurred? We have reached pi by 2, and like at this point the discharging starts, and at pi plus alpha the discharging ends. So this duration is pi plus alpha minus pi by 2. That's what, so this comes out to be pi minus pi by 2 is again pi by 2 and plus alpha. So this is my duration of discharge. Okay. Is it okay? Did you understand?
Yes, ma'am.
Okay. So let's go to the next problem. For the circuit and waveform shown in question 8, compute the capacitance for a ripple voltage of 5% of peak value of sinusoidal input voltage with 50 Hz frequency. So they have asked for the capacitor value. If we want to restrict the ripple voltage within 5% of our peak value, then what should be the capacitor value that we should use here, right? So this is also very simple. What we will do, so again the same diagram we need to refer. When the capacitor discharges, it provides the load current, right? I already told you, when it is discharging, the capacitor provides to the load. no current is drawn from the source. The source only provide currents when the capacitor is getting charged. When the capacitor is discharging, the current flows from the capacitor to the load like this in this loop. So we can say that during the discharging period, the capacitor current we can express like this: C dV by dt, right? This is the capacitor current. That is equal to V naught by R, because the output voltage is V naught and the load resistance is R. So V naught by R. This equation is valid only during the discharging period that I have highlighted. Okay. So dV naught is what? The difference in voltage. That is delta V naught, our voltage ripple, right? That is the difference that I already showed. This is our voltage difference from this point to this point. That is nothing but the voltage ripple. And what is dt? The discharging period. The expression we already derived, right? Pi by 2 plus alpha. But this is an angle. We need to convert it to time, right? Because this is dt. This is time. So if we do by omega, then we can get the time, right? Because we know omega times t. This is the time period, right? That is equal to 2 pi. 2 pi. Okay. So for finding out any time, if we know the theta, so the theta is this angle. So we have to divide omega. Then only we will get t, right? Omega t is equal to some theta. That theta is pi by 2 plus alpha. So to get time, we need to divide omega. Okay. So that's why there is a omega here. And what is omega? Omega is the angular frequency. Omega is equal to 2 pi f, where f is the frequency. F is already given here. Our f is what? 50 hertz, right? So if you do 2 pi f, you will get omega. So we have all the data. We have delta V naught, which is 0.05 Vm. We have omega 2 pi f, so 314 radian per second. So what we can do is, 1 second, just okay. So now, yes, another thing is we need the value of V naught, right? The average output voltage. What will be V naught? V naught is half of V max plus V min. So this is V max and this is V min. V max is Vm obviously, and V min is 0.95 Vm. So V naught also we have 0.975 Vm. So we have all the data for C. From this equation only, from this very equation, we can get the value of C. So we will transfer all these parameters to the right hand side, and we can get the value of C as 876 microfarad. Okay. This is the required capacitor value to restrict the ripple within 5% of peak input voltage. Fine.
Ma'am, could you please again this slide?
Sorry. What? For which part do you need explanation?
Oh, this part only, ma'am.
So till this equation you understood how I am getting
Yes,
this equation?
yes, ma'am.
Okay. So delta V naught, we know that it will be 5% of our peak voltage. Our peak is Vm. 5% of Vm means 0.05 Vm. And we also need V naught, V naught, because in the expression we also have V naught. This is the average of the output voltage. So there is some very small pulsation in the output voltage, right? And the average of that output voltage is simply the mean. What is the mean? How do we calculate mean of a quantity? That is max plus mean, half of max plus mean, right? If you have a quantity which is pulsating at a certain frequency, it has a maximum and minimum. So what is the approximate mean? The approximate mean is 0.5 times maximum value, its maximum plus its minimum, right? That is the mean of the quantity. So that's what we have found out. Maximum value is Vm, that we can see here, and minimum value is like this maximum minus the ripple quantity, right? So ripple was
Yes,
0.05 vm, so that's why v mean comes out to be 0.95 vm. So the half of these two, the summation, and then multiplying it by half,
okay.
that comes out to be 0.975 vm, right? And if you put all these values, then here in the denominator we have 0.05 vm, in the numerator we have 0.975 vm. So we don't need vm at all. Vm cancels out, and we know r is given already 200 ohm. We know what is alpha, that we calculated
Yes.
in the previous problem. So we have c, right? We can calculate c. Yeah, so I think we are running out of time. If I can't complete today, I will continue this in the next class, okay? Next tutorial session. So last problem is the design problem, okay? How to design a complete diode bridge rectifier. So this will be the typical specifications. The AC mains, which is 230 volt 50 hertz with a tolerance of plus minus 5%. Power output power is given 100 watt. Maximum source current is 1 ampere. Maximum ripple across the capacitor is 15.45 volt. All these data are given. Utilizing all this data, we need to design a diode bridge rectifier, okay? Design means you will have to select the components. What would be its voltage rating? What should be the current rating? All these things. While you will design a practical circuit, you need to design the circuit, right? To design the circuit, you need to know what should be its like limiting values, the limiting voltage, limiting current, and based on those design parameters, you will have to select the devices, right? So let's see how to design. First, we will see how will we select the capacitor value. That we already saw how to design the capacitor value. So here they have already given some tolerance, right? Some range, plus minus 5%, okay? So they have given uh, so they have given this tolerance of plus minus 5%. So the peak of the input voltage, we have a maximum peak of the input voltage, that is 1.05 times 230 root 2. We have a minimum peak that comes out to be 309. This is due to the tolerance. This is 1.05 and this is 0.95. This is the higher end, this is the lower end. Okay. So the grid voltage peak can vary between these 2 points. It can sometimes take a value of 341 also. It can take 309 also. It can also take a value which is in between these 2 points. Okay. And here so here again we have some annotations. These are the angles. So 0 alpha, pi, then pi plus alpha. And this charging duration, when the capacitor is getting charged, this duration is given as beta. Okay. So this duration is beta. So we can say that this VM2 point, this VM2 and this VM1, both these points are on the sine wave, right? And VM2 is lesser than VM1. VM1 is the maximum value. So Vm2 is Vm1 sine alpha, right? Because at this point the angle is alpha. So Vm2 is equal to Vm1 sine alpha, right? This we know. Delta V naught, it is given 15.45 volt. And this is nothing but Vm1 minus Vm2, right? Because we already saw maximum minus minimum, that gives us the ripple. So the ripple value is given to us. So we have the second equation. So solving these two equations, we can get this relation, right? Vm1 into 1 minus sine alpha is 15.45. So here I have taken Vm1 of this minimum value. So here the alpha comes out to be 71.8 degree. Okay, and this in radian. Now, as we have two different input maximums, this is the maximum and this is the peak value at the minimum condition. So we can have two different set of data, right? One is VM1 max, VM2 max, and V naught max, right? And another one is the minimum values corresponding to this peak value. And another set of data is corresponding to this value. Okay, till this point it is clear. How am I calculating? There are two sets of values because there are two different peak values that we have, because there is a range given for the grid voltage, right? That's why we are getting two different sets. Now the question is which set to take for designing the components. Should we take this one or this one? Which one should we take? We should take that one which will give us the higher value, right? We should take the worst case condition. Okay, so let's see. The process is same. The capacitance selection, we will follow the same process as we followed for the last question. We calculated the capacitor value, right? In the last question, we will follow the same procedure. The only thing is we need to select the data set, right? So again, I have written the same thing. So here we know during the discharging condition, the delta is C Vm1 square minus Vm2 square. This also we saw. This is the energy loss during the discharging period. That is what? Energy is what? Power times time, right? So this is our power and this is our time, right? This is the duration for the discharging. This is the discharging angle and by omega gives us the time, right? So like this we can find out this expression. Now we have divided it. Vm1 square minus Vm2 square. This comes out to be Vm1 plus Vm2, Vm1 minus Vm2. So half, and this portion, this gives us the V naught value, right? That we already saw. Max plus min by 2. And this portion is our ripple. So that's why I have written V naught times delta V naught. And right hand side is there. I have not changed anything. Okay. Here I have taken this set, this minimum set. Why? Because this gives us higher value of capacitor compared to this set. Okay. You can calculate it and see by yourself. So I have taken the minimum set and I have calculated the capacitance value 193 microfarad. Okay. If you have any doubt in the next tutorial session, you can ask me. Okay. I will explain. And here I have shown the capacitor RMS current calculation. Okay. So yeah. So I can explain this to the next class. Okay. How am I getting this average this RMS current of the capacitor expression? And here I have calculated the diode average current and diode RMS current. Okay. And also the peak inverse voltage of the diode. These quantities are important because while choosing the diode, we need these quantities. What should be the average current? What should be the RMS current? And what should be the peak inverse voltage of the diode? All these quantities we need to check. And we should choose a diode whose quantities are more than these parameters, right? Whatever quantities we calculated in the diode data sheet, all these parameters should be higher than this. We should select a diode that can withstand a higher RMS current and it can withstand higher peak inverse voltage. Okay. So I think most of the people have left. So I shall explain all these things again in the next tutorial session. Okay. Is it fine?
Yes, ma'am.
Okay.
ma'am.
So today I am ending the session. Okay. First I will stop the recording. Stop recording. Okay. So in the next